In this video, we are going to follow along with section 1.4 notes in your packet. So you'll want to turn to that page and fill in that page as we go through it. So section 1.4, we are looking at composition of functions. And as we talked about in class, what that means is we're going to take a value x and plug it into g. And then we're going to take whatever we get out of g and plug that into the larger function f of x. Another notation for that looks like the word fog, where you just have like a little baby o in between f and g. And again, what that means is put values into g and then put it into f for your final output. So to start our examples, first we have a linear function 3x plus 5, an exponential function 2 to the x. And what we're asked to do is put a 4 into g and then take that output and plug it back into f. So I'm going to first just come off to the side here and figure out what g of 4 is. And so I'm going to plug 4 into my exponential function, 2 to the 4th, and so that will end up giving me 16. From here, we're going to take this 16 and plug it into f. So I'm just going to copy down this linear function, and instead of the x, I'm going to just leave that with an empty set of parentheses. And again, we're going to take our output for g, plug it into f of x in place of x. Now we simplify. 3 times 16 is 48, plus 5 will end up giving us 53. So at the very beginning, we plugged in 4. At the very end, our final output of f of g of 4 is 53. So to do that again, notice on this one, they now have the order reversed. This says g of f of negative 1. So the very first thing, start on the inside, work your way out. I'm going to plug negative 1 into f of x to start. So f of negative 1, that gives me 3 times negative 1 plus 5. Negative 3 plus 5 will give us a positive 2. I'm going to take this 2 and plug it into g of x. So 2 to some power. And again, we're going to plug that in right there. Notice that's not a negative 2. My pen just kind of added a little extra line there. And we know that 2 squared is 4. So my final answer of g of f of negative 1 is going to give us 4. So if you have equations, you're looking for values, that's how you would do that. In our next example, we're going to use a table. So the first thing, g of 2, easy peasy, we know. We look at a table where x is 2, and we see we get an output of 3. Nothing new there. So our next value, g of 3, I'm going to use a different color here. g of 3, we come over here where x is 3. We see that our output for g is 7. That is the intermediate step that will help us find f of g of 2 and f of g of 3. So now that we know that g of 2 is 3, we're going to plug 3 into f. So looking at the table, when we plug 3 into f of x, we get out 4. For this one, we know that g of 3 is 7, so now I'm looking for f of 7. But looking at our table, we don't have x values that go down that far, and so that would typically mean that our domains are restricted and we don't have values. So for this one, we'll say does not exist, or none you could write. So we've done this numerically by plugging in numbers at the top. We've done this using a table, but now we're going to write an equation. And so let's say we had lots of numbers that we needed to find for f of g of x. we could just write a new equation, call it something else, in this case h of x, so it becomes a new function in itself. So when we do that, we're now going to take this entire equation and plug it into f of x in place of x. So I'm going to start by rewriting f of x, but in place of the x, leaving open parentheses. And now we're going to take g of x's equation and plug it in where x used to be. So we have negative 2x plus 5. And then next we need to distribute this 0.5 through so we can simplify the equation. So 0.5 times negative 2 will give us negative 1x. 0.5 times 5 will give us 2.5. And then don't forget we have this minus 7 right here. We're going to combine the 2.5 and the negative 7. So we will end up getting a negative 4.5. So our equation for f of g of x, the composition of the two, or you could call it the new equation h of x, is negative x minus 4.5. All right, so for the last one, as you're probably finding in Exploration 1.4, when we have restricted domains, not all values that go into g of x will have outputs in f of x. So keep in mind that whatever comes out of g, whatever comes out of negative 2x plus 5, we're going to put into f. Well, the only numbers that I'm allowed to plug into f of x are the ones between negative 7 and 13. So the only numbers that I want out of here are numbers between negative 7 and 13. Otherwise, I'm not going to be able to plug them into f of x anyways because of the restrictions on our domain. So we're asked to find, well, what numbers can I plug into g that give me numbers that allow me to plug them in to f of x because they're between negative 7 and 13. So what we do is we're going to take g of x and we're going to place it within these domain restrictions. And so this is going to look new to you more than likely, but it's going to be super easy to solve. And so again, anything that comes out of g has to be between negative 7 and 13 to be able to plug it into f. And so now we have this inequality that we need to get x alone. So we can solve it just like any equation. The one thing that you need to be careful of is if you're going to subtract 5, you now essentially have 3 sides to it to try and get x alone. So if you subtract 5 from the middle, you have to subtract 5 from over here and over here. So 13 minus 5 will end up giving us an 8. We have a negative 2x now in the middle. Negative 7 minus 5 will give us a negative 12. From here we know we need to divide by negative 2. And so when you first started solving inequalities, there was this one rule that if you ever multiplied or divided by a negative, you have to switch those alligator symbols the other way. So this will give me negative 4, positive 6. Now, if you forgot why that's the case, I'm going to come over here and explain that quick. Let's say that we have zoomed out like crazy here. Let's say that you have a statement, 3 is less than 7. Everybody agrees that 3 is indeed less than 7. But let's say you multiply both sides by a negative, and that's an okay thing to do because you do it to both sides. You're now left with negative 3 is less than negative 7. That is no longer true when you multiply or divide by negative numbers. So to make this okay, whenever you do that, you have to flip the sign. Oops, and I added a little something extra there. You have to flip the sign the other way. That way the comparison is still true. That's what happens in this step here. When we divide by that negative 2, we have to flip the alligator symbols the other way. I just noticed I was missing a bar there. Now if you want to write this differently, you could put the negative 4 way over here, turn the alligator symbols around, and these two are the same statement. basically what it's saying is our x values that we can plug into G need to be between -4 and 6. And as long as we only plug numbers between -4 and 6 into G, I'll get numbers between -7 and 13 back out. The one thing to keep in mind is that G had its own restrictions. And G of x only wanted numbers between -3 and 10. So all of the numbers, including -3 and 10, were in G's domain. Well, we just found out that the numbers that were allowed to plug into G to then make it okay to plug into F are between -4 and 6. And I'm actually going to place that -4 over just a little bit more. And so these are the numbers that we're allowed to use that will work for f of g of x. The issue is that we have some conflicts. So yes, we can plug in numbers -4 to 6 into G to make f of x happy, but right away at the beginning, we're not going to be able to plug in -4. That's not allowed. So our final domain has to make both of them happy, and that's going to be between -3 and 6. And if you were to graph these like we were doing in class, this is where you would see the graph appear, is between -3 and 6.